Today I'll be talking about the mechanisms of SN1, SN2, E1 and E2 reactions. So SN1, SN2, E1 and E2 reactions are substitution or elimination reaction. S stands for substitution. So let's start with the first type of substitution reaction, SN1. S stands for substitution, N for nucleophilic, and 1 stands for unimolecular. It's called unimolecular nucleophilic substitution reaction because only one molecule is involved in the rate determining step. Bimolecular nucleophilic substitution is designated as SN2, where S stands for substitution and nucleophilic, and 2 stands for bimolecular. In this case, it's bimolecular because 2 molecules are involved in the rate determining step. And then you have the unimolecular elimination reaction. It's represented as E1 because only one molecule is involved in the rate determining step. And then we have bimolecular elimination reaction in which 2 molecules are involved in the rate determining step, and it is symbolized as E2. So let's start with the first one, unimolecular nucleophilic substitution reaction, SN1. So the rate determining step involves one molecule, and so it's unimolecular. It's a two-step reaction with 2 transition states. If solvent is involved, then it's a 3-step reaction. The carbocation is formed as an intermediate in SN1 reaction. The carbocation is planar and it's sp2 hybridized. The nucleophile can attack the planar carbon from front side or the back side. When solvent is the nucleophile, then the reaction is called solvolysis. Because the carbocation is formed, there is a loss of stereochemistry at the reaction center, and this results in a racemic product. So let's look at an example. So this is an alkyl chloride. This is a carbon-chlorine bond. In a solvent, it can give a carbocation. In a polar protic solvent such as water, it can give a carbocation. So I have this model made so that it's a little bit easier to explain. So this green is the empty p orbital. This carbon is the carbocation because it has the empty p orbital. This is the carbon. This, let's assume this to be the phenyl group, pH, and this is the deuterium. And then you have the methyl group here. You have 1, 2, 3 hydrogens attached to a carbon. So that's the CH3 group. So you can see right here that the carbocation is planar. Okay, so it's planar. And water molecule, let's consider this to be the water molecule. So this is oxygen, and these are the 2 hydrogens. And these 2 green sticks are, let's consider them to be the lone pair of electrons on oxygen. So the lone pair of electrons on oxygen is going to attack the empty p orbital, which is on the carbocation and the carbon. It can attack from the top as it cannot attack from the bottom. So if it's like this, then it can attack from the front side or it can attack from the back side. and because the carbocation is planar, the resulting product, since there's a 50% chance of front side and back side attack, you'll get a racemic product. So the product that is obtained will be right this. So this is the methyl group right here. This is the benzene ring. This is the deuterium. And this is the water molecule that attacked the carbocation. So this carbon is now become tetrahedral, and this has a positive charge. A base is going to come, remove this proton, and leave the lone pair. So oxygen will now have lone pair of electrons on it. Okay, so this is the product, and this is just one of the chiral molecules. You can have it this way, and you will have chiral two enantiomers. And if you want to learn about stereochemistry in enantiomers, please refer to my video on classification of isomers, where I explain what enantiomers are. Okay, so there'll be loss of stereochemistry because of the formation of carbocation, and the carbocation is planar. So let's look at the second type of reaction. This is the bimolecular nucleophilic substitution reaction. So two molecules are involved in the rate determining step. The nucleophile attacks the reaction center from the side opposite to the leaving group. And this is a concerted single step reaction with one transition state. A new bond is formed partially, and an existing bond is broken partially in the transition state. This results in the inversion of stereochemistry at the reaction center, resulting in a chiral product if you start with a chiral starting material. So let's take an example right here. Okay, so this is the starting material. This is the starting material, alkyl halide. So this is the carbon atom, this is the bromine atom, carbon-bromine bond, this is deuterium, this is hydrogen, and then this is the methyl group. 1, 2, 3 hydrogens attached to a carbon. So this is the methyl group. So this is the starting material, and then you have OH group. So this is the oxygen, and this is hydrogen, and this is the negative charge. So it's going to attack. So if this is the molecule right here. Okay, this is the carbon. This is the carbon, and this is the bromine. So the bromine is right on the side, and the OH group is going to attack the carbon center from the side opposite of the carbon-bromine bond. So it will come on this side. Okay, so that's how it's a backside attack. And then you will get a transition state. So in a transition state, you will see, let's make a transition state and see how it looks. Okay, so this is the transition state. So this is the methyl group right here. Okay, this is the methyl group right here. So you have 3 hydrogens attached to a carbon, methyl group. You have the carbon bromine bond. This is the bromine atom. This is the OH group, oxygen here and hydrogen here. And then you have the hydrogen and deuterium. So you can see that this is the transition state, and the bromine and the OH group are on opposite side, and then the bromine atom is going to leave, and you're going to get the product. So the product will, let's make the product. So this is going to be the product. So you have the methyl group right here. It's attached to this carbon. You have deuterium, and then you have the OH group, and you have the hydrogen right here. So this is the product. So you'll have a chiral product, one single enantiomer, since you have started with a chiral starting material. So that's the characteristic of SN2 reaction. So SN2 reactions, if you start with a chiral starting material, you will end up with a chiral product. And there'll be inversion of configuration. So let's move on to the next type of reaction. It's called the unimolecular elimination reaction, because only one molecule is involved in the rate determining step. It's a two-step reaction with two transition state, and carbocation is formed in the first step as the intermediate, which then will lose a proton to give a carbon-carbon double bond. So the base abstracts the beta proton from the adjacent carbon, and the resulting product is an alkene. It's a double bond, and the most stable alkene is formed by Zatsev's rule. So let's look at an example. In this particular case, you can see this is an alkyl halide. This is the alpha carbon, and this is the beta carbon. So the beta carbon has 3 hydrogens attached to it. So in a solvent such as ether, and in presence of triethylamine, it will undergo a E1 elimination reaction. So what is happening here is a carbocation is first formed by loss of the chloride. This carbocation is planar, and then a triethylamine molecule, which is a base, will abstract the proton. The proton is on a beta carbon. This is the beta carbon atom. The carbon atom next to the carbon bearing the positive charge is called the beta carbon, and an alkene is formed. So the most stable alkene is formed. So let's look at the bimolecular elimination reaction. In this case, 2 molecules are involved in the rate determining step, and hence it's called bimolecular. The base abstracts the beta proton from the adjacent carbon at the same time as the leaving group or atom departs. It's important that the proton, beta proton, be anti-periplanar to the leaving group for the E2 elimination to occur. If the beta proton is not anti or on the opposite side as the leaving group, then the reaction won't occur. So the reaction, just like the SN2 reaction, this E2 reaction is concerted. It's a single step reaction and has one transition state. The new bond is partially formed, and an existing bond is partially broken in the transition state. So there's partial positive and negative charges involved in the transition state. The product that's formed has a carbon-carbon double bond, and it's an alkene. So let's look at an example. So in this particular case, we have the hydroxide you have the beta proton. This is the leaving group. So you can see the hydrogen that will be abstracted is opposite to that of the chlorine. So that's very important. That's called the anti-periplanar. The OH group is going to abstract the proton and the electrons will flow. This is arrow pushing, so the flow of electrons is always from electron rich to electron poor, and then this will leave. The chloride is going to leave. That's a leaving group, and an alkene is formed. So in summary, for E2 reactions, you need to have the proton that's abstracted and the leaving group in anti-periplanar configuration. The product that's formed is a double bond for both E2 and E1 reactions. Carbocation is formed as an intermediate for SN1 and E1. And the product obtained from an SN2 reaction has inverted configuration if the starting material is a chiral. Racemic product is formed from chiral substrates via an SN1 because the intermediate is the carbocation, which is planar, and the nucleophile can attack from the front or the back side, giving a racemic product. So a molecule will always give one major product under a given set of conditions. How can you predict whether it will be an SN1, SN2, E1, or E2? To find out, please refer to my video on how to predict the type of reactions. Thanks for watching. Like and subscribe.